Quadratic equations are used to model several different types of situations. Some they model nearly perfectly, and others they model only over a certain period and then experience model breakdown. We'll be taking a look at both of those examples. But before we take a look at examples of quadratic models, there's some important concepts in quadratic models that we need to remember. Number one, it's always very important to identify what your independent and dependent variables are. Number two, whenever you're asked to maximize or minimize, this implies finding values at the vertex, because we remember that a parabola either opens up or down. In the case of it opening up, the minimum value, the vertex is the minimum value. In the case of it opening down, the vertex is a maximum value. So in either case, if you're maximizing or minimizing in the context of a quadratic model, it's important to remember that that implies you're finding values at the vertex. Lastly, the value of c. The value of c in the equation y equals ax squared plus bx plus c is what we call the initial value, the y-intercept. In some cases, that value is significant in that it communicates specific value to us, specific information to us. We'll take a look at what context that comes up in a little bit. So let's dive into our first example of quadratic equations or quadratic model. So this first example has to do with the flight path of a projectile through the air, in this case, a baseball. So the quadratic function h of x equals negative 0.004 x squared plus 1.12x plus 3 models the height in feet of a hit baseball, that's in h of x, after it has traveled a horizontal distance of x feet. So we have two different variables here, x and h of x. X is horizontal distance. H of x, h is our height, which you could understand as vertical distance. Question is this: what is our independent variable? What is our dependent variable? Because it's written in function notation here, h of x, it communicates to us what the independent and dependent variable are. The independent variable is x, which equals horizontal distance. Conversely, our dependent variable is the variable h. We can write it as h of x in function notation if we want, and h of x is equal to height. In other words, the height of the ball is dependent upon how far it has traveled horizontally. It is important to include units. Horizontal distance is in feet, and our height is also in feet. Important to keep that in mind. So with those two variables identified, let's move on and now answer the next question about our quadratic model. It says this: what was the height of the baseball after it has traveled 40 feet horizontally? So we're asked to find the height after it's traveled 40 feet horizontally. The important piece in regards to identifying dependent and independent plays itself out in this problem, because we are given some information and then asked to calculate some information. In this case, we're given that it has traveled 40 feet horizontally. Up here we defined, or we identified, our horizontal distance as our independent variable x. So we're being told that x is equal to 40. In this problem, it's also asking us what was the height. That's the piece that it wants us to find. Height in this case is h. Well, h of x, we just identified that the known quantity is that x equals 40. So in essence, this problem is asking us to find what is h of 40. In other words, what is the height after it has traveled a distance of 40 feet horizontally. That's our x. So h of 40 would simply mean we plug 40 in for our x's in our quadratic model. So our equation becomes negative 0.004 times 40 squared plus 1.12 times 40 plus 3. So at this point we can get a calculator out and plug this in and see what this value ends up equaling. So back to our home screen here. Let's take a look. We have negative 0.004 times 40 in parentheses squared plus 1.12 times 40 plus 3. It gives us a height of 41.4 feet. 41.4 feet. So after the ball had traveled 40 feet horizontally, the height of the ball was 41.4 feet in the air. Great. Let's move on to the next question it's asking in regards to this quadratic model. The next question says this: what was the height of the baseball right when it was hit? Right when it was hit. Well, there's a couple ways we can look at this problem. One way we can look at this problem is that first off, height is what we're looking for. What's the information we've been given? Well, we've been given that we want to know the height right when it was hit. Well, how far has the ball traveled horizontally right when it was hit? Well, if it's right where it was at the initial hit, we know that our x is equal to 0. That's the horizontal distance it's traveled right when it was hit. So in essence, we are being asked to calculate h of 0. h of 0 is equal to what? It's equal to negative 0.004 times 0 squared plus 1.12 times 0 plus 3. When we simplify this, we won't even need to use a calculator here, because since both values, or the value of x, is 0 in these two locations, the first two terms cancel out, and you end up with h of 0 equals 3. h of 0 equals 3. So the height of the baseball right when it was hit was 3 feet above the ground. Now, we could have approached this from the standpoint of understanding it in terms of an initial value. We made the statement at the very beginning that the value of c in your equation, which for us is this value here, the value of c represents your initial value in the units and label of your dependent variable. For us, it's height. So the value of c, as you notice, everything else disappears when x is 0. The value of c tells you your initial value. And the phrase right when it was hit is implying the height at the very beginning, the initial value. So we could have, instead of doing all the calculation of finding h of 0, just known that the value of c in a quadratic equation gives you your initial value.